Am I supposed to have 2 of these?
Yeah, we probably will have definitely more. If you want to, please.
I mean, I'm not going to turn down free food.
It's okay. Because it's ice cream, right?
Yeah.
It just melts and then it's for nothing.
Alright. Ah,
He's alive!
you want an ice cream?
Oh, there's one.
Yeah, you didn't show up Tuesday.
Oh yeah.
We have some. Maybe if you take the food first.
I can find you for this. Oh, I see what's going on here.
I'm
Okay.
all alone.
Welcome to the last meeting in the semester. If you are here, you are in chemistry 476/676. It took me a half year to remember it. So there is a last meeting where all class attendees demonstrate how the skills acquired in the course did help in characterize materials and chemicals from computational point of view. So the idea of the course is to combine together the theoretical part, the practical skills, and communication skills. And you had enough theory, enough practical skills at evenings and nights, and today it is a time for communication skills. So scientists communicate their achievements to another scientist. Everyone is welcome to ask challenging questions. The reason for each presentation is to be able to stand the question. The program includes 3 chapters. One on the interfacial charge transfer, which is a very general problem. Another is on biochemistry, and then there will be a couple of talks on chemical reactions. So when you are coming to the podium, please plan on speaking not longer than 6 minutes. We will assign 10 minutes for each talk, out of which 6 are for presentation and 4 are for answering questions. There is there are forms where you can write down your feedback. How do you like what you hear? Of course, final decision will be taken by myself, but it will be a really helpful input to see the main goal of scientific activity, how the presenter finds the path to the brains and hearts of the audience. In case you are seeing Microsoft PowerPoint and Windows Computer for the first time, which I doubt, you find your number in the schedule and your name on the title of the file. You click twice and launch it to presentation style. If by some reason movies are not working, do not panic, explain them by waving hands. They should work, but just be morally ready to anything unexpected.
What are we grading out of? What are we grading out of?
First?
No,
So-
like 1 to 10, like 1 to 5.
A, B, C.
Oh, okay.
More questions? If no, let me invite to the stage Master of Science, Vijay Shah, who has recently completed his degree, and he will present computational modeling of the interface between silver and silicon. Floor is yours.
All right, thank you for the introduction. As Professor Killian said, I'm Vijay Shah, and I'm going to be modeling the interface between silver and silicon nanoparticles. So nanoparticles are small materials that consist of, in the case of our simulations, an inorganic core, meaning that the material or the atoms that the core is made out of are not made out of carbon, hydrogen, etc. Rather, they're made of silicon and silver in our simulations. Each of these nanoparticles are covered in different types of chains made up of carbon, nitrogen, and hydrogen atoms. And nanoparticles have been shown to exhibit size-dependent properties, in particular optical and electrical properties. So optical properties include both photoluminescence and surface plasmon absorption. And surface plasmon absorption allows the nanoparticle dispersions to exhibit different colors when they're viewed with different types of experimental apparatuses. And for electrical properties, the organic chains covering the nanoparticles can actually hinder the conductance of the nanoparticles. And overall, there are many practical applications of nanoparticles, including to photovoltaic cells. So the objective of our research is to determine the best electron donor and best electron acceptor, and use this pair in order to help facilitate the charge transfer between nanoparticles. So in particular, we will be looking at the density of states, the absorption spectrum, and partial charge density in order to characterize the charge transfer between different states of our nanoparticles. So on this slide, you can see a couple of different images for our model. So on the left-hand side, we have a silicon nanoparticle. The yellow atoms are representing the silicon atoms, and the turquoise atoms represent the carbons, and the gray atoms represent the hydrogens. On the right-hand side, you see a silver nanoparticle, where now the pink atoms represent the silver atoms, and the chains are made up of different molecules such as carbon, hydrogen, nitrogen, and oxygen. And for the purpose of our simulations, which were run in VASP, the silver and hybrid models were oxidized 5 times. So this means that from the neutral model, we actually removed 5 electrons from the model when we were running simulations on them. And this was to explore different oxidized states for our model. But for the purpose of this talk, I'm only going to be talking about the simulations where we removed 5 electrons. So here on this slide, you can see 2 more different models, one being where some of the organic chains are removed from both of the nanoparticles. And on the right-hand side, you see a large ligand connected to the silicon nanoparticle. And both of these are different morphologies than when we just consider the silicon nanoparticle and the silver nanoparticle, as well as when we take both of these models and place them in the same input file. So we are really looking at 5 different models, 2 lone nanoparticles, then both of the nanoparticles brought together, both of the nanoparticles moved closer to each other in order to model the interface between these nanoparticles, and finally, where we have a long ligand attached to the silicon nanoparticle. So on this slide, there's a quick movie. It's going to be very difficult to see, but this is optimization of the silicon nanoparticle by itself. So this was run using, I think, 1,000 ionic steps in VASP in order to optimize the silicon nanoparticle. And you can see the total energy after optimization, as well as both the alpha and beta orbital band gap. So the alpha represents the band gap between, or for the red states in the density of states, whereas beta represents the filled blue states and all of the states below 0 on the vertical axis. And then finally the Fermi energy as well. So we can see that there are some electrons in the conduction band here, and this is likely because the model was not oxidized. So further work could be done in order to actually oxidize the lone silicon nanoparticle. and remove electrons from the conduction band. And we'll see a consequence of not oxidizing this model in a couple of slides. Here on this slide, this is the density of states for the silver nanoparticles. So we did oxidize this model 5 times. And you can see, again, the energy after optimization as well as alpha and beta band gaps. You can see that there are, again, electrons in the conduction band. And finally, Fermi energy as well. And on this slide, here's a model where we took both nanoparticles and put them in the same simulation and optimized the entire model at once. So we have both of the nanoparticles are being optimized at the same time, and the total energy after optimization is actually a little bit higher than the separate energies after optimization for the silicon nanoparticle and the silver nanoparticle, which signifies that the binding energy is actually positive, and therefore the two nanoparticles would want to actually repel each other when brought close together. And again, we have density of states here. You can see that there's not really a distinct difference between the valence and conduction bands in the density of states. The highest occupied states are very close to the lowest unoccupied states. So on this slide, we have a couple of different absorption spectrum. And for the first 3 plots, there's a very large peak near 0 energy, signifying that incident light would have to have a very large wavelength in order for an electron to move to a higher energy state. And then on this lower right-hand plot, you can see that there are peaks at a higher transition energy, signifying that ultraviolet light can actually excite electrons from a lower state to a higher state when these electrons absorb photons. And here on this slide, you can see a couple of charge transfer plots. So on this left-hand side, these are the charge transfer plots for the HOMO and LUMO orbitals. And then on this model on the lower left-hand side, we have the HOMO orbital is represented by pink, and the LUMO orbital is represented by gray. And on the right-hand side, we see that there is some charge transfer between HOMO -4 and LUMO +5. However, there still is not too much. So further work could be done in order to actually characterize different morphologies and different oxidations and determine where the most charge transfer will actually occur, for which models they will actually occur in. So in conclusion, we see that the density of states, absorption spectra, and partial charge density plots do not actually help in facilitating the charge transfer between states when our models have 5 electrons removed from them. And in the future, work could be done in order to determine which morphologies and oxidations will actually yield the most charge transfer between states. So with that, I would like to thank Professor Dimitri Killing, Dr. Yulan Han, Aaron Forty, and Nerskin USD Cluster for computational resources. Thank you.
Okay, but thank you, Dave. So there is time for a couple of questions. I have one. So what is the reason for absorption close to 0 energy, and do you see, if it is not real, what are the practical ways to remove this artifact?
Yeah, so I'll go back to the plots, right here. So the question was what the significance is of this absorption spectra looking, basically having a peak at 0, how it could be removed and if it's real or not. So the peaks near 0 right here in the spectra were actually a consequence of having the HOMO and LUMO states be very close to each other. So the band gap was essentially 0, which means that electrons did not need to have much energy in order to go from one state to the next state when you're trying to excite the electrons. And in order to actually combat this, one would need to oxidize the model more or in other words, remove more electrons from the model in order to have these peaks appear at higher transition energies.
Can you go back?
Yep.
More? Yes. So probably you wanted to repeat the same verbal explanation about this figure.
Right. Yeah. So here we can see as well from this figure, you see that HOMO and LUMO are very close to each other, so the band gap's essentially zero, and the same thing actually occurs right here. So you can see that this final state that is occupied is only partially occupied, and right next to it is an unoccupied state. And similarly, in the beta orbitals, there's a partially occupied state right here around negative 7.5 electron volts. And then finally, for the silicon nanoparticle by itself, again, there's a partially occupied state in the alpha orbital. And then very close to it, you see that there's a completely unoccupied state. So those would cause the absorption spectra to have peaks at low energy.
Okay.
Did you look on the localization of HOMO-LUMO in that system? Is the HOMO-LUMO in the same system or in different quantum dots?
Yeah, so we did consider I did do a simulation where this model was actually not spin polarized.
Not this one, I mean next one.
Oh, the next one?
Two system, yeah, I mean two.
Yeah, so yeah, we didn't actually I didn't actually have time to consider the original model and determine like the original HOMO and LUMO for this system. That would have been something that would have been good to compare to though.
And what is the distance between these two silver nanoparticle and silicon part?
It's very low, I believe.
No, I mean, yeah, and the two model system, two
Yeah.
pair system. I forget the amount.
Here we go. Yeah, so are you talking about like center to center distance, surface to surface separation?
Surface to surface.
Okay. I believe that was approximately 5 angstroms. It was somewhere between 5 and 10 angstroms.
So do you think that they're supposed to have any interaction between the in that distance? Any charge transfer possibility?
Charge transfer, most likely not. But yeah, interactions like binding energy, that would be present. So binding energy would be a little bit positive or a little bit negative at that distance.
Yeah.
Okay. If there are no more questions, let's thank Vijay once again. And let me invite to the stage Landon Johnson, whose presentation title is so long that I cannot pronounce it. So it's very, very technical. But to my understanding, he's continuing the discussion of interface between donor and acceptor groups. And he's looking how the ability of charge transfer depends on the linker between them.
Yes, that is exactly what I'll be talking about. So specifically, I'm going to be looking at the boundary between cesium, lead, bromide, perovskite, and 2 different types of titanium dioxide. So I guess why am I looking at this? In order to make a solar cell out of perovskite, you essentially need to surround it with a hole transport material and an electron transport material. The reason for that is that, I mean, if you shine light on a perovskite, cause excitations, that's all fine and good, but you're not going to end up getting any current. You're not going to be able to build a potential difference between your 2 terminals unless there's an inherent preference for the direction of that current. So what you want to do is set up a system so that when you do create excitations, the electrons will naturally want to flow one direction and the holes will naturally want to flow to the other direction. So in particular, I'm looking at this interface here. So these are the 2 models that I'm working with. We've got the titanium dioxide on the top and the perovskite on the bottom. And we have a isopropanol linker group in this case. And we have hydroxyl linker groups in this case. And we're just looking at the differences between these and just trying to characterize them generally. So these are some densities of states, I guess, of the separated systems and then combined. So these are all the isopropanol model. And these are all the hydroxyl model. So the perovskite in both cases are essentially identical. There are some slight differences between the titanium dioxide, but largely they have the same structure. you can see that when you do combine these systems, you actually get a different shape, I guess, of the density of states. You end up losing a lot of these states from the titanium dioxide. It suggests that there is a significant interaction between the two when you put them close together. So some of the things that I can pull from that data are just the total energies of each system, the HOMO and LUMO gap, the Fermi energy. And we can see that in both cases, you do actually reduce the HOMO-LUMO gap. But in the hydroxyl case, we see that there is actually a smaller gap, which means that you'll be able to get a wider frequency of solar radiation that you could potentially convert into electric current. When I calculated these out, this one was like 494 nanometer wavelength, I believe, and this one was 430 something. So it's not a huge difference, but it suggests that there is at least something of a difference there. So these are just some plots of orbitals, and then these are one-dimensional potentials that are obtained by integrating over the X and Y dimensions just to yield essentially a one-dimensional probability of finding an electron in some region. So in the isopropanol case, you can see that the, I guess you can't really see that. So these are the, I can't remember which is which, I think it's the same between them. The blue orbitals are is the HOMO, the red ones are the LUMO. And you can see that those are both localized on the titanium dioxide in the isopropanol case, whereas in the hydroxyl case, you actually do have, you have the HOMO in the perovskite and then the LUMO would be found in the titanium dioxide. This would be preferable because as you do create an excitation, if the electron jumps into the next orbital, it will actually move over to the titanium dioxide, whereas in this case, the charge doesn't actually end up going anywhere, so you don't get that desired property that we're looking for. So this suggests that the hydroxyl is probably better in that regard as well. This is kind of a schematic of what I was just talking about, where the lowest energy jump would be just from titanium dioxide to itself, whereas in this case, you would actually transfer the charge over to the titanium dioxide from the perovskite. So I was only able to get one of my molecular dynamics jobs to run without failing immediately. And this is the density of states after doing molecular dynamics at 1000 Kelvin for, I think, like 329 femtoseconds. So I guess the general shape of the density of states doesn't change that much. You just kind of get more states over in the conduction band. But it does actually seem to increase the range over which you can actually get absorption. You kind of end up getting this whole bit here that doesn't make an appearance in this end. And these two density of states are the same ones from before. Yeah, I guess I don't really know what else to say about that at the moment. And this is the movie of that molecular dynamics run, I guess. So, in conclusion, the evidence does seem to suggest that the hydroxyl model is the more suitable model for photovoltaic applications. Just because you do have a smaller energy gap, you do have actually charge transfer happening, or at least it's more likely to be happening. I feel like there's one other thing, but I can't remember what it is right now.
Okay, then the last thing is to give round of applause. Any question? Yes.
I have just technical questions. I was not able to understand what is your really. Can you show me all this structure? What is your hydroxyls and what is your isopropanes? Is it ligands on a?
Yeah, it's strictly
ligands on a. The surface is your titanium dioxide surface, right? And the quantum dot is your perovskite, or backward. Which one is which one? I'm completely confused. What is your quantum, like the confined structure? What is it? Is it titanium dioxide or perovskite?
I guess I'm not sure what exactly it is that you're trying to
I'm also not sure what we're talking about. So you have a surface and you have a zero-dimensional structure. Agree?
Zero-dimensional structure?
Yeah, because it's confined from all three directions. No periodicity along neither of these axes, so it's zero-dimensional structure.
Okay.
What we usually call nanoparticles or quantum dots or nanocrystals. So what is your nanocrystal? Is it titanium dioxide crystal or it's a perovskite crystal?
Oh, this would be the crystalline structure. I guess I'm thinking about this as just basically taking a chunk of like a thin film.
So where is your titanium dioxide?
This is the titanium dioxide.
So you have
here.
quantum dots made from titanium dioxide.
Yes.
And
Okay,
the surface is made from fumes or whatever, surfaces of perovskite.
Yes.
Then again, your orbitals, if you go back to the orbitals here, so you on the one side, your orbitals look like they're completely localized on your nanocrystal,
Yes.
on a nanoparticle, right? And on the second, is it like hybridized? Like you
What
have
is red
orbitals
and
both on the
what
surface?
is color codes?
So the blue in this case would represent the highest occupied orbital, I guess. I don't know if that's
And red?
like the red would be the lowest unoccupied. So if
So you
the
have
lowest level excitation would mean that an electron would go from the blue band to the red band.
okay. So in the first case, you have both HOMA and LUMA on your nanoparticle, and on the other case, you have one being localized on the nanoparticle, and the other is localized on the surface. And this is what you call a charge transfer.
Right.
But my understanding, their energy of absorption is very different between these two materials. So you can easily tune the absorption just, let's say, on the range of your perovskite or on a range of your quantum dot, because it looks like your energetically they're very different, right? So you can imagine that you're really exciting just one system rather than both of them.
Okay, so you're assuming like a fixed
Like I'm
energy
assuming
that
that
you're
in the
exciting
case
with
when you have your HOMA
pairing
being
them
on
based
one
on that
material,
energy, I guess.
when your HOMA is on one material and your LUMA on the other material, this transition is optically inactive. It's you cannot excite such state because it's optically inactive, right? You can excite the states which are either both localized on a perovskite, and then it would be perovskite transition, or both localized on a quantum dot, and then this would be your quantum dot transition. And then the idea is when you excite one material, then the charge transfer should go from not between HOMA-LUMA, but kind of inside the band, from unoccupied state if it's electron transfer, or from occupied state if it's a hole transfer. Like I don't understand your definition of a charge transfer. Looks kind of usually, and what's the purpose of, like this charge transfer state will not provide you any good things for the current. Because your idea is that you, like this construction of the material is based on the idea that you use one as absorption material, as a synthesizer, and the other would be your contacts. And it looks like probably the three-dimensional surface or whatever, two-dimensional surface would be your contact, right? And then your titanium dioxide would be the synthesizer in this case. And then you need a charge transfer from the titanium dioxide to the either in a both occupied state or both unoccupied states. I mean, after you optimize it, of course, you create a hole, and then hole goes. Then hole transfer means electron from one material goes to the whole state of that material. But not like you exciting this charge transfer state, because such charge transfer state would be optically inactive.
You might have to run through that a little bit slower for me. I guess that was kind of quick. So the perovskite is the optical absorber in this case. The titanium dioxide is not in and of itself optically active.
Then what's the purpose of your titanium dioxide?
It's essentially, I guess this is sort of what you would want, is so that you have an electron in here that gets excited and you want it to get naturally pulled away from the perovskite into the titanium dioxide.
What for?
To create a current.
Current? Where?
Or potential difference.
You just create a charge on a quantum dot. That's it. It's not called current.
There would be a terminal attached to the other end.
To
the
quantum
titanium
dots?
dioxide.
To titanium dioxide quantum dots will be something like you will have some lead on a titanium dioxide.
Well, I mean, when I actually made these, I made thin films, so it wasn't necessarily like quantum dots, I guess.
I think
I mean, physically, I guess I don't know exactly how I would make this.
you probably need really look on a Gretel cells just to get the main concept and understand the idea why people really have this kind of molecule and the surface or whatever nanoparticle and the surface.
Okay.
Because I think conceptually you're really doing something not what is supposed to be for the not at least for the solar cells.
Mm-hmm.
Because again, in solar cells, the idea is that you excite in one material, right? And after excitation is done, then the charge transfer happens from that. Let's say if you excite, you have excited electron on the valence band, on the conduction band, right, of whatever, of the molecule. And then this electron will go to the, usually will go to the semiconductor, right? Which has plain kind of, the wave-like electronic structure where you're really kind of creating a current and then it goes to the leads. Or it can be hole transfer, then your hole, which means electron from titanium surface, will be taking the place of the excited hole in your molecule. So this is how the Gretel cells works. In your kind of suggestion how these guys should work, I'm completely lost what exactly is the purpose of your titanium dioxide. And why you need really to excite, like as I said, like this excitation which you say is good because it's a charge transfer state, it is a charge transfer state, but such state is optically inactive. Because your orbitals not really overlap and your dipole moment for such transition should be very, very low.
Okay.
More questions? It was not a question, it was a comment.
Well, I think conceptually the idea why and what the motivation behind all these things looks kind of completely messed up.
More questions? Okay, then let's thank Landon once again. So the next presentation is the last one in the sequence of solid materials, and it is slow transition to softer materials. So it is by Daniel Ramirez, and he will tell another story about wet halide perovskite surfaces with different surface absorbers.
Thank you, Dimitri, for the kind introduction. So I will be studying same thing similar to Landon with 2D thin film perovskite, but in this case I'll be seeing the effects of two different ligands placed on such a structure. So we begin. So basically the overview, I'll just give you a little quick background, purpose, results, so on and so forth, basically standard on all this. So basically perovskites, they were discovered in 1839 in the Russian mountains by Gustav Rose, but they weren't named after him, they were named actually after a mineralogist named Lenin Perovsky. So that's where the name came from. Crystal structures, normally ABX is a molecule containing ABX3. In my case, I do have the same type of structure as Landon, where I will be having a study of cesium, lead, and bromine as my ABX3 molecule. And what makes perovskites really unique and interesting is that different cations can be embedded into the structure, and that allows for different types of materials. Basically, the goal is trying to find that correct one that will make it flow perfectly for what we need it for. And I'll mention that a little bit. But basically, what makes a perovskite, well, what makes a cell is the doping, the P and N doping. And in this case, what Landon was talking about, how P types are usually electron hole carriers, and N type semiconductors are electron carriers. The thing we gotta make it flow, make it good, is have a junction where we have both a P type and N type work perfectly together. So quick little explanation. An N type, as I said, are basically electron rich. They sort of donate their electrons to the structure to make it considered an N type, so it makes the structure electron rich. And a P type semiconductor, as the little picture says, it's electron hole carrier. So whenever that electron gets full, the hole will be displaced there will be a hole after that electron moves into there, and it will just keep repeating itself and over. And well, the purpose, well, perovskites are actually quite exciting when compared to conventional semiconductors that are out in the market today. They pretty much have a high conversion rate, and that's sort of the purpose, is just to try to find which structure will make it work best. And so one of the things I first did was one of the ligands I first looked at was an acetic acid deprotonated, or otherwise known as just an acetate ion. So in this case, this is what my structure looked like. It's just that's my 2D film. It's a 2x2x2 simulation cell with the acetate ion attached to the surface, with the purple being cesium, the gray being the lead, and the red being my bromide. So when I look at my density of states, I sort of notice at the -2 electron volts that there's a little white space around the area. This is analogous to a p-type orbital. No, it's not a p-type orbital. I mean a p-type semiconductor, which means it can be readily oxidized, and it makes this a ligand that pretty much can determine itself as a electron hole carrier. So in this type of structure, this is what we call, I guess, a p-type semiconductor, and this ligand would be perfect for that. And whenever I ran this cell, I found a band gap of about -2 eV volts, or electron volts. And the other ligand I looked at was ethyl ammonium. So in this case, you see some density past the conduction band, and in this case, as basically vice versa to the other one, this actually makes this a great N-type semiconductor, which makes it a pretty much great electron carrier. So whenever we put those together, well, gee, I apologize, I have a simulation on the ethyl ammonium attaching itself to the surface for the perovskite, and that's sort of what it looked like. I was hoping to be more ambitious and try to have a simulation for all three ligands. The third ligand I'll be talking about in a little bit. It's just jobs are still queued up in nurse. The moment everybody in class knows how tricky that is to get your jobs to run, but that's beside the point. So the more important one is when we look at both of these together in combination. So whenever we attach our acetate ion and our ethyl ammonium together, we have a band gap of 1.5 electron volts. Our density states over there, and we still see some type of density across the band, but that's probably due to the N-type ligand, our ethyl ammonium. And well, after that, we were able to find absorption, and I'm not sure whether people in the crowd like electron volts or wavelength. I'm more of a wavelength person, but I don't discriminate against electron volts. So basically, we have a high peak around the visible range. It's usually in about the green range at 500 wavelength, 500 nanometers. I apologize. And if you do like electron volts, we have a high transition at about 2.5. And well, whenever it comes to comparing our HOMO and LUMO gaps, apparently me and Landon like to use the same type of color coding. So blue, for this case, blue is my HOMO, and the red is my LUMO. So we see most of the HOMO and the HOMO density coming from ligands, which in this case, what's interesting is that during the simulation, our ligands ended up bonding to each other, which is kind of hard to explain for me in my part.
Do they create the hydrogen bond between oxygen and hydrogen?
Excuse me?
Do they create a hydrogen bond? This is the reason why they bump to each other.
Did he create a hydrogen bond? I think so as well, because right here, this is my carbon. It's bonded in the middle, so. But
looks like your hydrogen is really attached towards the oxygen, and if you measure this bond, it probably would be on the range of the hydrogen bond. Like, and
yes.
this probably explains why your two molecules interact with each other rather than with the surface.
Yeah, that's something I guess I didn't really look into too much. I kind of put this together last night. I wish I had more time to look at it, but that helps. Something for me to look forward to and upgrade my knowledge on it. But yeah. So, well, one thing I guess was kind of a little tricky for me was I have no idea where how I ended up getting say a homo orbital in the middle of my surface. That was something I guess I gotta look into and look down upon it. Well, I guess look at more of the orbitals and levels. I only got a chance to look at the HOMO and LUMO due to time being an issue. But besides the point, we also did find a LUMO orbitals on the surface of the structure, along with some on the methylamine, particularly on the amine site, which is I guess kind of a little interesting to look at. But conclusion, when I was trying to find out, say, the binding energies, I was doing correction after correction after correction. When I first started off, I had a binding energy at about negative 22.5 eV volts, but after doing a couple of quick simulations, I was able to down that to a 12.5 electron volt. But based off the literature, it's more around 5 electron volts, so I got to spend a little bit more time to try to find out I could zone in on that value. But as I said, I wanted to be more ambitious and show a molecular dynamics of the junction together. That'd be a lot more interesting. But the job is submitted, and if you really want to know, I can get back to you on that. And possibly what I could add to this research is I wanted to see what would be the effect of, say, adding a longer chain instead of ethylamine. I want to try like a propylamine and so on and so forth. I don't know if it'll be much better or nothing, but that's something to look forward to. Or messing around with the other ligands, such as formic acid instead of acetic acid, and seeing the effects of that, and playing around what would happen with all those. And my last slide is I like to thank the HPC cluster in South Dakota for allowing us to borrow their resources. The nurse cluster too, that's really was useful. Thank everybody in class too. I like this class sort of because we helped each other out, and most importantly, Professor Killen for helping us all semester long and not ripping his hair out whenever we asked him a question.
Okay, let's continue. Other questions to this fine gentleman? Oh, lots of questions.
Oh, I just have one on the very first slide. You said ABX something.
Yeah.
What does that mean?
What does this mean? Usually ABX3, what that means is obviously our X just means it's a halide. So I'll get back to that. Work out. So ABX3 in this case, A and B are usually our cations, and A is usually surrounded in the middle. It's pretty much one of our heavy metals. Our B is also a metal, but that's going to be surrounded. That's going to be surrounded a lot more around it, and our X is just our halide. So basically, our A will sit in the middle, then our B will bind to our halogens, and so on and so forth is what happened, and looking like a little orthorhombic structure. Anybody else?
Mr. Barton.
Question about density of state. Can you go to one of your density of states diagrams? What is zero here on your orbital energy diagram?
What is zero?
Yes, what is zero
0 electron volts.
versus what?
Oh, versus density of states.
Does your zero have any physical meaning here?
Does it have any physical meaning?
How did you choose a point to be zero?
How to choose the point to be 0? In which sense?
energy is arbitrary value, right?
Yeah.
So your 0 point you can choose wherever. You can put 0 as HOMA, you can put 0 as your 1s orbital from the core electrons, right?
Mm-hmm.
So how did you choose this?
Would it be?
Did you choose it? Maybe a program choose it for you?
Well, how I plotted that density states was a script that was given to us, so I guess I didn't really look into the definition of that too much. Apologize.
So, what does density of state shows? Density of which states?
The densities of, well, I guess the homos.
Orbitals.
Yeah.
Okay. And where do you get the energies of orbitals?
The charge density.
Can you elaborate on this a little bit more? Where, just practically, as a user, where do you take it from? Where these energies are?
Well, I guess where they're more likely possible where an electron would exist at.
Do you know what is Fermi energy?
Fermi energy, yeah, but I just guess I can't come up with a definition
Any
of that.
definition? Okay, let's say if you talk about metals, what do we call Fermi C or Fermi level? Does it help?
Talk about metals, I guess the transition energies.
Can you point Fermi energy on your disk of states? Just by finger.
Just be all red. What is it?
By finger or by given number.
Basically red.
2? -2? Or something different? Point once again. You do not see it.
-6.
No. Fermi energy is one value.
Oh, so
Not the range.
oh, so we just right there at the range -2.
Okay. And where do you get energies of orbitals? Not how they're computed, but where you are getting them from.
Where I'm getting the energies from the orbitals. On, I guess, the surface of the atoms.
No. Which equations are solved in order to give you these energies? You can browse through the menu and not menu, through the write-up, and in your writing or in writing with someone else, tell where they are coming from.
The Conchon orbitals?
So their energies, where they are coming from?
From the structure.
No. Instructor doesn't give you energies. You are extracting it from somewhere.
Maybe the class can help. I hope that this answer, probably at least some of you might know.
Energies are eigenenergies of the Milken value problem, so they're fictitious. So iteratively produces these eigenenergies.
Do you agree?
Yeah.
Good. More questions to Daniel?
So what's 0?
Okay.
Do you have a density of states plot for just the naked perovskite?
I do, but I didn't include it in my slide. If that's
But you have a
It's in a-
book in your hands.
We have the links to the
No.
oh well.
Without any Ligands, you have such.
I just guess that these values were just obtained from the calculations as they are given from your software, right, VASP or whatever you were using. And technically, the scripts which you probably were using to create the doors, they should have also maybe include the information on the energy Fermi, which actually gives you the energy where you have all levels below the energy Fermi are occupied, all levels above the energy Fermi unoccupied. And technically, usually it's very common when people choose zero to be equals to the energy Fermi. Means you take your energy as calculated, subtract the Fermi energy. And Fermi energy is also usually is provided by this software. And I guess you probably just forgot to include this value when you were plotting your figures, right? If you subtract the energy Fermi, then zero will be exactly the energy Fermi. And usually, if you have very symmetric valence and conduction band, then energy Fermi means your zero should be really in the middle. If there is some asymmetry, and usually we have much more dense states on a valence band rather than conduction band, then Fermi energy usually is shifting towards the more denser states. So means usually it's really kind of shifting towards the HOMA, not exactly in the center, but going close to the edge of the valence band.
Yes.
But in your case, I guess your zero has no really any meaning. You just forgot to subtract the Fermi energy, right? Or you really think that zero is where the Fermi energy, so it's so close to HOMA?
What about like Koopman's theorem, like the ionization potential for the HOMO?
Ionization potential not equals to Fermi energy.
Not equals to Fermi energy, but the absolute values of these energies.
Yeah,
It's important. It's physical.
well, if you can use ionization potential as your zero if you want to, but
No.
but this is not the division. I mean, then your scale will be completely different, right? Because your ionization energy, it's energy needed to free the electron, to make the electron completely free. It's really huge energies in this case, right?
Let me conclude the discussion. The eigenvalues of Kohn-Sham equation are computed without additional approximations. All approximations are included in DFT. And those energies in approximate way, according to Koopman's theorem, provide energy of ionization and affinity, energies of orbitals. The density of states that Daniel is showing are literally the energies that are computed by Kohn-Sham equation without shift of the 0 point energy. It is not shifted to the Fermi. And maybe it is what Professor Parent originally wanted to ask.
But then your zero, if you claim in this, then your luma equals to the affinity energy, right? And then it's
It
zero.
means that in this system it is yes.
Affinity energy is zero.
Yes. It
But
is,
this is also what people measure, and it's never zero.
this model doesn't have ligands and substrate. So it could be consequences of the structure. But you are correct in that, in LUMA state, it will be almost free electron, according to taken approximations. This is what is generated by software. So, more questions? Not, oh, please.
So, can you show your image of the two ligands?
Yeah.
Surface. And while you do that, do you know what the poster child perovskite is?
With the poster child
Poster child perovskite.
Well,
So if you had to name a perovskite, which one would you name?
well, it's sort of some of the ratings I've done, they've pretty much done methyl ammonium and
No, just the perovskite itself. Can you
Oh.
name a perovskite? Pick a perovskite. What would you name?
oh, based off like the okay,
I'll help you out. How about barium titanate? Right? You consider that to be a perovskite.
yeah.
Has no halides. Barium titanate contains no halides. So X in your ABX3 formula,
Yeah.
the X is an anion. Okay,
This is an
and
anion.
often it's oxide.
Okay.
Okay,
Yeah.
Okay, so to your two ligands on the surface, do you have that slide?
So oh, this is this one there.
No, you showed one where you tried to show.
Are you talking about like the video?
Electron densities? Where you had CHEM orbitals, a HOMO and a LUMO. Okay. So you have to excuse my geriatric eyeballs. I can't see this for sure, but it looks to me like, is there actually a what's the interaction between the ethyl ammonium ion and the acetate ion? I can't see what's going on there.
There's a small, as Spelana mentioned, there is a H bonding in between the acetate ion and the carbon nearest to the amine group.
So from the ethyl ammonium ion, which heavy atom would be the best hydrogen bond donor? Nitrogen or carbon? The methylene carbon or the ammonium nitrogen?
It'd be the nitrogen.
So why do you suppose there's a hydrogen
But there are oxygen there.
hydrogen bond between a methylene carbon and an acetate oxygen?
No, it's not carbon, it's a hydrogen there.
No, the question is
hydrogen bond is the sharing of a hydrogen atom between two heavy atoms, right?
Oh,
And then
okay.
he's illustrated it between a methylene carbon and an acetate oxygen, if I'm seeing this correctly.
You are.
Does that seem chemically reasonable?
When I noticed this too yesterday, not really, but it was probably due to a couple of things. I probably didn't let it optimize all the way. So if I did use my chemical intuition, then I would continue the simulation again. But since it's presentation day, I had to show what I had at the time.
Okay.
And it's, like I said, it's something I pretty much gotta look.
So you can confirm that according to your chemical intuition, you would expect something different.
Yeah. But,
Yeah, in fact, you would make a salt, right?
yeah.
You make an ammonium acetate salt. So that not just hydrogen bonding, but the Coulombic interaction between the acetate and the ammonium ion would be quite strong. Right?
But
Yes.
If you sort of think about non-bonded interaction.
both are ions, so you have plus on your ammonia and you have negative charge on your carboxylated, whatever it is.
Yeah, I mean, yeah, that's true. My nitrogen on that ethylamine is a positive charge, and the acetate ion is negative charge. But I still would have seen it. I think how he was trying to say it, how they would bond to each other, because I mean there shouldn't be any charges in the carbon, so I don't see why there would be hydrogen bonding in between here. But it's something that I wish I had more time before I could discuss it.
So maybe the follow-on question is, we're looking at a two-dimensional projection of a three-dimensional system here. So just to be clear, is it possible that the ammonium ion and the acetate ion are at different depths? Are they really as close together as they appear to be here?
When I remember in my simulation, I think I had them set at about 3 angstroms apart from each other. So
Okay, so they are. Right.
We need to go on the program, but let me add, because it's really exciting discussion. So in practical applications that Daniel didn't cover with all depth, the ligands are covering surface of semiconductor at one monolayer, 100%.
Yeah.
And they are densely packed on the surface, not loosely, not they do interact. More questions?
Okay, I get that. It's just he's only showing two molecules or two ions, I guess. So it's a little hard to tell what the third dimension looks like. That's my only.
But there is definitely formation of the bond between lead, is it lead and oxygen, right? So kind of a coordinated bond. There's one molecule, and then I don't know, nitrogen is coordinated with whatever, is also lead and what. Like this molecule is not independent, right? They still interact with the surface, right? Or they disattaching from a surface and you really kind of losing the interaction with the surface and they start interacting with themselves. And maybe forming a salt or something.
Yeah, I could see that because whenever I ran that single simulation on just the effluent, I mean, it was orientating itself, it was positioning itself so the nitrogen was closest to the surface, so meaning that there could be some type of bonding in there.
Yeah, but just distances. If you just measure the distances, this will answer a lot of questions right away.
Okay, so if there are no more important questions, let's conclude the very fruitful discussion on the presentation by Daniel. And no more solid surfaces from now on. So Alyssa Roberts will make first step into the biochemistry area.
First and only, right?
She will share her experience on toxic environment for cell membranes.
Okay, so my presentation is on the impact of hydrogen peroxide on the phospholipid bilayer. So my system, just to start out, is gigantic. So a lot of the calculations that were run were only being able to run for a short amount of time, but we'll get there. Okay, so previous studies include in VASP as well, so like the same system that I was using. They were done with a smaller simulation, so the same phospholipid bilayer as the one that I used, but only done with 4 solvent molecules. So there's not like anything that happened in that could have possibly been a coincidence rather than, not a coincidence, but like just because there wasn't too many solvent molecules rather than more oxidation by it. It was done in an aqueous solution, so there was hydrogen peroxide present as well as just plain old water molecules. And what they concluded from that was that the presence of the water molecules causes the hydrogen peroxide to decompose into 2 different species that do not interact negatively with the phospholipid bilayer. And so I wanted to look a little bit more into that because that didn't seem right, that hydrogen peroxide would not affect the phospholipid bilayer negatively. So I decided to make a different system. But what the software that I used was VASP for everybody else in the class. I used periodic boundary conditions to simulate a bilayer. So I reproduced it in the direction that would make a bilayer sheet, which then would be wrapped around to form a cell. So this is just supposed to represent like the outside of the cell. And then I used 34 hydrogen peroxide molecules instead of just 2. So the system is a lot larger, and it interacts more with the phospholipids, 2 phospholipids, no water molecules. And then I put it at 1500 K, which is extremely high. And I recognize that, but since there's, I don't have very much knowledge on this, so please don't ask me a question on it. It's supposed to simulate, well, it's supposed to overcome the quantum tunneling that would occur naturally. And I don't know much about that, but just giving it the extra temperature would allow it to get over the activation barrier and be able to interact like it normally would in these situations. Okay, so this is just I know most people know what the phospholipid bilayer looks like, but this is the chemical composition of it. This is just a carbon chain with the glycerol, phosphate, and then the choline at the top. So that's how I arranged my bilayer, but the fatty acid, so it's like 2 instead of 1. So anyways, so this is a side view of it. I have a different view as well because this is kind of hard to see the distinction between the 2. But basically, this is the fatty acid chain. That's the glycerol, phosphate, and then the choline. And then these are the peroxides. This is after the first round of molecular dynamics, so that's why there's some loose hydrogens or protons. I'm not sure, but it's one of the 2. So that's why it's not like 100% perfect. That's just making. And this is a side view, so you can see that the chains are separated and they're not overlapping. I just thought that it's easier to see two different views, so you could actually get an understanding of like how they're interacting with each other. Okay, this is after the first heating of it, so not molecular dynamics. But the one thing that I wanted to just show here is there is a electron density right there. So they are bonded, and you can see that by this. Oh my gosh, I'm forgetting the word. By this picture, there we go. And then after, I don't know why it's so grainy, but this is after the first round of molecular dynamics, and so even though it doesn't, like the system, the software isn't showing a bond there, there's clearly is still a bond there because of the electron density that's present. And then, so this is my simulation. Each molecular dynamics step took about an hour to run. So there's a few, but it takes a long time, so I couldn't go past what I have here. So the main thing that I wanted to point out is, I think it's here on this, yeah, right here. If you look here, you're going to see the bilayer. Okay, there you go. This is what the main part that I was looking at as far as the glycerol is hit by a molecule, and it completely dissociates the fatty acid chain from the head, which would completely disintegrate the entire polar head of the molecule. So that was my main discovery through this, was that, I mean, it would obviously impact it. One thing that I did want to address, I didn't put the graph in here because I didn't think it was worth it, but you can look in my paper if you want to see the graph of temperature. The temperature starts at 1500 K, sorry, and escalates dramatically to about 50,000 K, which is extremely significant and completely like that's not possible. But I think that is because of the periodic conditions, so that it's enclosed and it's basically burning the molecule, which would, like, all the bonds and the breaking and the forming and all that stuff is just causing mass chaos in the system, which would increase the heat dramatically. And so you can look into that a little bit more in the paper. Okay, that was. I don't know. I was a victim of collaborative editing, so this is not my doing. But here's a close up of the I'm sorry, this is really funny. Of the bond breaking. So yeah, it just gets sad. And then this is density states. This is going to be the same issue that we talked about earlier, as far as this is not centered on the difference between the HOMO-LUMO gap. This is just what the software reproduced. So yeah, but this is the actual energies of these orbitals, rather than them being edited, since they're arbitrary. I don't think it really matters, as long as this is the difference between, or the middle of that is the difference between the HOMO-LUMO. And this is what it looks like. What I'm not fantastic at interpreting these graphs, especially for a system like this. But what I was talking to Dimitri about was that the bilayer should be transparent, but this indicates that it is not, because of the wavelength that it absorbs. So what we were thinking was that this was the density states, and the chances of the HOMO-LUMO would be between the phospholipid bilayer to the titanium dioxide, not titanium dioxide, we could hear more about that, hydrogen peroxide. And yeah, so those are basically my conclusions. It's just the hydrogen peroxide would break down the phospholipid bilayer. And then it increases the heat dramatically, so it'll probably burn the cell before, if that has anything to do with the decomposition of it. And then without the presence of water, which is what the simulations previously have shown, peroxide would be harmful, or at least at a higher concentration. And that's it.
Okay, let's thank Alyssa for her great effort to simulate by DFT systems which are typically not simulated by at this level of theory.
So technical question. So you apply periodic boundary conditions for kind of making your bilayer being bigger, right? So which means that any kind of, and when you optimize, you didn't let optimize yourself.
I didn't have a chance to
I mean, to optimize. Well, you didn't optimize your structure.
No, I couldn't. Just because of the time, I just heated it up and then I ran another dynamics on it.
So you run just dynamics without optimization at room temperature. And, okay. But my point is that because you still have a cell size, right? So and your lipids are really very soft. They really want to fold and do something like that probably, right? But if you already constrain them in this, and they cannot go beyond these boundaries, right? So you really put a lot of, I would say, order in your system, probably artificial order, which might be really kind of affect your overall results with interaction with this other molecules.
I'm sure it did, but I
understand you.
Yeah,
were
I
in
could
the
put
conditions
more
to
in
do at
there.
least something.
Yeah, so I'm sure that affected at least the activity of the hydrogens, first of all, because you could see they were going all over the place. I'm sure that was because of the periodic conditions, and I'm sure there's other effects of that in there, but I thought I'd give it a shot. That's kind of.
More questions?
That was actually kind of similar question.
Okay, I noticed 3 in a row.
Pick somebody else.
Yeah, but your system doesn't look like periodic. Is it periodic?
It is periodic, but it's not like I didn't show it in here. It's like in VAST it's periodic because the vacuum is only 1 angstrom. So then it's in.
And I'm thinking actually why you run then 1500? What is the significance of that 1500?
I just chose a temperature that was pretty hot. that's the only significance of it. I just wanted to make sure that I didn't run a couple of faulty calculations because we were limited on resources. So I was like, you know what, I'm gonna give it a really high temperature and hopefully that'll be enough. I'm sure in future experiments, if this was worth pursuing, then I could lower the temperature and see where the lowest temperature would be, where it would still incorporate quantum timeline.
We have a few more questions.
Well, when you showed the simulation,
Mhm.
the graphical simulation of the breaking of the glycol bond,
Yeah.
it appeared to me it's like a ballistic collision.
Yeah. Yep.
Basically, an inelastic collision that transferred energy to some piece of the molecule that just went immediately beyond the dissociation energy and exploded. Is that do you think a chemically reasonable way to think about?
Oh no, for sure not. I don't claim that is what would actually happen. If I had more time to really plot what was happening, I would try and figure out where. In previous studies, they have looked at the hydrogen bonding, the hydrogen transfer throughout the fatty acid chain, and that would end up causing an imbalance because there'd be unsaturated carbons, and then in the end, that would end up disintegrating, basically causing a dissociation from the fatty acid, from the head, and that would end up causing. So that would most likely be, if I were to keep running these simulations, the cause of it. But this worked too, so I just kind of took it and ran with it. But for future things, I would definitely not look at, ballistic collision for that.
So what do you think is happening to the hydrogen peroxide? So you point out in your conclusion that hydrogen peroxide decomposes in the absence of water, according to the simulation.
Yeah.
So what is the decomposition product of
I
hydrogen peroxide?
believe that it is decomposing into I'm so sorry, I didn't know. Hydroxide without a negative charge, so as a radical species, which would interact with that.
Hydroxyl, it's called.
Yeah, but sorry, anyways.
Okay.
And with water present, it decomposes into H2O and O2, which would not negatively impact the cell. So, I mean, that's what I at least think would happen, but not sure.
So if you were to take a cell culture and start dropping in hydrogen peroxide, do you think the cells would survive?
Probably not, no.
Okay. So water doesn't keep hydrogen peroxide from damaging cell membranes. That's why I'm asking these questions. I'm trying to figure out how water plays into the thinking about the chemistry. What do you think hydroxyl radical would do to the molecule? What is hydroxyl radical famous for?
I do not have the chemical background to answer your question.
Okay.
Yeah.
Fair enough.
But I would love to learn and figure it out. But that's kind of what I came up with for right now.
Thank you.
Question about your phospholipids. What is the chemical structure of those guys?
Okay, so this is a different software than I use. So this is the choline here, so that's the nitrogen, as was seen here.
Okay. Those are fully saturated?
No.
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 Okay. So.
There's a kink in both of them. I think you can.
Okay.
Yeah, right here.
Okay, so that's an unsaturation.
Both of them are unsaturated, yeah.
Okay, so if they're unsaturated, why might it not be transparent?
I guess that I have no idea.
Are alkenes transparent?
Are you saying it? No.
Well, you said you didn't do geometry optimization, right?
Mm-hmm.
So that's probably why it's not the right geometry, probably.
In optimized geometries, are alkenes transparent?
I don't know.
Well,
I've never computed
The
it out
absorption
for
probably
an
stays somewhere in
optimized
the UV range, right? So the absorption starts somewhere in the UV range for the alkenes. So for any other wavelengths, it should be transparent up to the way it starts absorbing, right?
So there are several things that one would do even for this large system for targeting optical properties. So as Alyssa already mentioned, optimization, and second, using hybrid functions, which are much slower, better in mix.
Yeah, but it's not unexpected that you would see that there is a reasonable bandgap.
Oh, okay.
You get a homoluminal excitation from having the alkene like that.
Actually, can you comment on your methodology and how much you can trust your band gap?
Okay, well,
What is your functional? Which you
I believe it's the PV functional. I'm pretty
What
sure.
kind of this function? What type of the function is it? Well, Dmitry something mentioned about hybrid functionals, right?
So you should answer.
So it looks like if he mentioned about hybrid functions, this is definitely not a hybrid functional.
Okay.
And I don't know, did you have a discussion about choice of the functionals and the effect of functionals on your electronic properties?
I don't know. I would have to look more into it.
Well, I guess again, there are all people like so. No one were using any other functional except except the PBE functional for this class. I see. So the question about functionals were not really a question. You trust that what you can get with your PBE functional is really good for any kind of systems you were calculating, right? Or there are any other ideas from the class?
That's obviously not true. It's just with the time constraint, I don't think we necessarily learned enough to mess with the functionals, nor be able to do it ourselves. That's with me personally.
At least it's the first thing which you do when you calculate. You need to figure out what is your methodology, right? And you need to get at least some ideas what kind of type of functionals you choose, and what to expect from these functionals. So when you take a pure GGA functionals, pure DFT functionals, are you expecting that your band gaps, your energies could be underestimated? Yes? What if you use Hartree Fock? Are you expecting your band gaps could be also underestimated? Then what they will do? Accurate?
So this was part of the class. What will be the consequence of applying Hartree Fock to the same system? Like, where would it change the gap?
Yeah.
Where? To higher or lower value?
Alyssa, show it again.
Where?
Good just.
Oh,
Yes.
larger.
Okay.
Because it's an approximation.
So Hartree Fock will kind of give you two big gaps. The GGA functions typically provides two small gaps, right? And that's why people add some Hartree Fock portion to the GGA, which we call hybrid functionals, which will kind of balance both of these errors and end up with something more reasonable. So that's why having your band gaps lower than it is expected in experiment, if you're using your PBE, it doesn't matter which system you use, is a very typical error, is a well-known error. You should not really expect it to be, if you get it very close to experiment, then something is wrong with your calculation.
More questions to Alyssa?
One more question about the periodic boundary conditions. So if I understand this right, you have it set up so that there's an infinite number of the same system that you're modeling here.
Yeah, and I made an error in my paper. I said it was periodic in the Z condition, and that's not right.
No, it's just X and Y.
Yes, I believe so. It's either just X or just Y. I'm pretty sure it's just one of the other.
Making a line.
Yes,
The line
exactly.
goes for infinite.
I think so. I think that's how the system is.
It's your boundary condition. So you have an infinite number of the fatty acid chains, and then each of them are having the peroxide shot at the same time. Is that how this is working? Okay.
Yeah.
That's probably why your temperature goes insane.
Yeah, that's what I was. Yeah, because it just it explodes basically. The temperature just becomes extremely hot.
Its nearest neighbor exploding at the same time.
Yeah, exactly.
Explosion
Yes,
going
so
on.
she's really having a periodicity,
Infinite explosions.
which is really artifact. Right?
Yeah, I mean.
Okay, last chance for questions to Alyssa. If not, thank her once again. And until the booking is valid for this room, we have 2 more talks. So now we are departing from surfaces and from biochemistry and going more to inorganic chemistry and catalytic reactions. So the presentation by Braden Brian, we'll go over the iron porphyrin.
Thanks for the introduction. Yeah, so I'll be discussing some preliminary data on a chlorite decomposition reaction to produce, say, molecular oxygen and chlorite. So there's a class of enzymes, chlorite dismutases, that are known to participate in such reactions, such decompositions of chlorite. So, interesting to note, molecular oxygen is somewhat difficult to create synthetically. So it's very cool to see something in nature that catalyzes this reaction. So that's a very important reason why we should be looking at this.
It's really hard to hear you.
But the chlorite ion itself is a negative ion, but throughout the simulations, I've explored different charges for different things as well. Okay, so in the actual enzyme itself, obviously it's a very complex system where just a small part of it, usually called the pocket, enzyme pocket, which houses a heme macrocycle. So an iron center macrocycle with 4 adjacent nitrogens, and usually some axial ligand. In this case, it's an imidazole connected to the long arm. But the enzyme itself obviously is composed of thousands of atoms, and we cannot obviously do that using density functional theory or any ab initio methods. So what we're considering here is a very simplified version of this. So we just have the macrocycle itself, the iron in the center connected to an imidazole linkage with a part of an arm. And to kind of make it a little bit more realistic, I've fixed these two carbon atoms in space in all 3 dimensions, such that this imidazole is a little bit more rigid than it would be if I was to relax those degrees of freedom. Because this carbon atom itself is connected to a long chain here, which would offer a little bit of rigidity for that line. And in addition, there's stuff above that I'm neglecting as well that will probably make big consequences in the overall reaction in reality. But again, we're using a very simplified model here, so we just want to model the reaction at the surface, at least in parts. And that'll make more sense when I get to it. So, what reaction is happening? So we're looking at chlorite, so oxygen bonded to a chlorine bonded to another oxygen, usually in a single anionic form. So it's hypothesized and also seen in experiment that the oxygen, or one of the oxygens, will bind to the iron, and then we'll go into some transition state, possibly one where you have a hypochlorite ion stabilized by some nearby amino acid chains, mainly arginine that's kind of sitting above the surface. But that has not been necessarily seen in experiments to my knowledge. And then, also interesting fact, it produces a peroxide linkage, so an oxygen-oxygen bond that has been seen in experiment. And then it would undergo another last step to produce molecular oxygen and chloride. So we're interested to know if this reaction can take place, or which direction this goes, if it's like a homolytic bond cleavage event or a heterolytic bond cleavage event. This is unknown and is the main instigation for doing this. Okay, so here's my one methodology slide. So we're using VAP software to calculate all of these equations. So we're using the CHEM single particle equation. And so if somebody has questions, I can go into detail. Oh yeah, interesting to note there's an error in my paper write-up. There should be a square marking here, but there is not. But so I've calculated optimized these structures separately, and I've tabulated them. So if you look at the total energies, which is most important here, chlorite likes negative charges. So the negative total energy implies that it's a more stable structure, of course, and so if you have more negative, it's kind of implied that it's a more stable structure. So like I said earlier, chlorite here is known to be in a single anionic form usually, but as you can see, it's not the lowest number here. This could be an artifact of the results from the DOT. We could move to higher level results, and this may change. So it's important to note that we could use higher level methods at the time, and I will probably be doing, I actually have some calculations right now doing optimizations for higher level theory. One more thing to note about this is the fourth column here, the magnetization changes, of course, when you have different numbers of electrons. We'll come back to that in a second when we talk about those things. So here's the density of states for each of the structures. So you can see that the bands themselves are pretty distinct, separated by, for the positive ones, separated by many electron volts difference. So more interesting to note, the ones that should be look a little bit more reasonable. So the absorption spectra are shown here. And for chlorite, this one we see, because the occupations are so close, we see a large bump in the absorption energy because it's occupied next to unoccupied, so that's discussed in a previous presentation. So, well, we can calculate the just the macrocycle by itself. And so we get a structure that looks something like this. And so you have partially spin up, partially spin down, occupied state. Since we do spin polarized calculations, we have the ability to do that. And if you analyze this approach to spectra, you can pick out some peaks that are indicative of say, porphyrin rings, but I haven't done too much analysis into that for this purpose. Now we can look at the combined structure. So, like I said, there's reaction pathways that are hypothesized and some seen in experiments. So this first one on the left, we just have an oxygen binding the hypochlorite and the iron, and so that's shown here. And then the next stage, which has been seen in experiments at peroxide linkage, we have that shown here, and another state as well. We have shown here. This is maybe the hypothesized transition state. So the hypochlorite may be sitting above this macrocycle, stabilized maybe by nearby arginine charged amino acid, and absorption spectrum as well. But so more interestingly, we can run dynamics to shoot a chloride ion at the iron, say at different angles, at different velocities, to simulate how this reaction might progress in nature. The potential energy surface, of course, is very complex, but knowing picking a vector approach and choosing different velocities, you can kind of estimate the activation barrier for this reaction to occur roughly. And so some observables you can look at is the bond distances, of course, of different atoms to see if things are participating in bonds as evolving in time, and also charge density, partial charge density, so the HOMO and the LUMO orbitals visualized as a progression of time and their localization. Okay, so here is the first video. So the chlorite ion is approaching here at 60-degree incline to the plane, in the same direction as it would in real life, or from the same plane as it would in real life, coming between the two carboxylic groups. So that's where the pocket opens up to the outside world. So you see kind of the artificial bond, of course, but the iron has kind of snatched that oxygen from the chloride, and the chloride has some residual momentum, of course, so it goes on, but retains this oxygen. So this is the first step in the hypothesized reaction. And so now this is where the hypochlorite might be stabilized sterically or coulombically by a nearby charged species, and then it may flip around to create that peroxide linkage that is also hypothesized. So looking at this from not a nature example, so looking at it in steps, right? So if we've modeled this first step, now we can think, so we can take that product and maybe shoot it in the reverse direction or from other angles as well to get the second step. So kind of eliminating maybe the transition state structure itself, just looking at what could happen at step 1 and step 2. And so here is another one that didn't work out, 60 degrees again. So here we have 60 degrees again. It did not work out because this one was at a higher velocity. And so it's kind of a double-edged sword. You can't have a too high velocity because it'll bounce off and possibly break the bond in and of itself, but this oxygen won't attach. But too low, it'll bounce back or reflect off of the potential energy surface. So it's a real kind of fine-tuning to get this right. And so here is a very preliminary result of, say, HOMO and LUMO orbitals as a progression of time. So of course this is very staggered because I only took every 10 steps. I calculated the electronic structure and computed the charge density. So I can make this much smoother if I was to look at every step in most dynamics. but it's interesting because some of the, and you can see this in the paper, I think maybe a little bit better. Some of the charge densities look very nice, but they jump very quickly over a 10-step region. So this is really not that informational if I take that many steps. And also the time step in the molecular dynamics should be reduced. Currently it's at 1 femtosecond. For reaction type processes, this should most likely be reduced to gain better electronic convergence between steps. This is my main. It's the same thing. So, so like I said earlier, this is more or less a meaningless plot, but you can make a lot of interesting plots. So Alyssa had temperature and total energy. Here I'm computing bond distance between the iron and the oxygen nearest, and the iron and the chlorine. And so just from this, you don't have to look at any videos. You can see that a reaction took place as these two are initially equidistant. And this one separates, and this one has some oscillatory bond. So conclusions, we successfully modeled the first stage, not quantitatively, but very qualitatively. And so now we can restart simulations with hypochlorite coming back in, say from another direction, to try and form that peroxy bond that we're interested to see. And so we can do all this at higher level if we would like, but qualitatively it seems to agree with what we think, except for the total energies in anionic systems by themselves. So to sort out the possibility of spin flip processes is also very interesting. And very interesting for this reaction, because in any transition metals, of course, you can go high spin, low spin. Given it happen, so you can use non-collinear spin calculations, which is much more expensive, but it allows for an interesting magnetization vector as a time-dependent magnetization vector, which is might be very interesting to look at as well. So that concludes my talk. Any questions?
Okay, let's thank Braden.
Can you go back to the chloride slide where you were showing the absolute energies? Sorry, slide numbers are always useful. Yeah, this. So how are you determining those energies on the left with chloride? Oxidation.
That's a really good question. Well, the total energy of the system is obviously given as a result of using these simulation packages, the software VAST. But the total energy is calculated different ways. DFT, of course, is calculated as a function of the density. So it's just a contribution of all the different terms, so potential terms.
But what molecules specifically are you modeling? You're just modeling the ones on the left?
Oh, sorry. Yeah. So this system, maybe I should bold separate this. I have two lines here to separate, but this system contains 1, 2, 3 values, and then I have a new system here.
Yeah, that's the chloride. But when you're modeling it, you're setting it up as a chloride with 2 oxygen bonds, and then you're just setting the total number of electrons?
Yes, that's exactly it.
Does that give you meaningful numbers?
So you may, let me reformulate the question. Do you have any suspicion in this number? And if you do, what are the possible mechanisms that can affect the precision of these numbers?
Well, so these calculations are done in vacuum. So this, I think this could be one thing. Stabilization could occur between molecules. That's what you're getting at.
Would a free electron have any energy contribution to this number? Does adding an electron intrinsically change the number, regardless of the state of the system? If you're just adding in an electron.
I mean, there's completely non.
If it were completely non-bound, would it change the value for your total energy? Does a non-bound electron have any energy?
Should.
Okay.
So you're saying normalization to compare better. That's what you, okay, I see what you mean.
The electron has to come from somewhere, right? So if you add an electron directly to any system, the total energy is always going to go down, always going to become more negative. And that's what you're seeing here, right? As you reduce, the number always goes down. Doesn't matter what the orbital energies are, because even if the orbital energy would be too high, the electron will just float around, not bound to anything. And the electron energy will still become more negative. So that electron has to come from somewhere. So you need to balance it out by having a corresponding oxidation somewhere else. Model of oxidation. So one way to do that would be to say, to correlate one of these ClO2, say the ClO2 minus to the change between the ClD, where this mutate is going from -1 to 0, and the -1 to -2 over here. And then you can see what the total energy change is when you do that electron transfer. And that can give you a good idea of what's going on. Typically, you would use ferrocene for this, because if you reference to ferrocene, it's very good. You can compare it to experimental data. And so this is not showing that the ClO2 minus is so stable. And you can tell that because the number goes down a very small amount when you go from the -1 to the -2. So it's not a very big amount when you go from the neutral to the -1, or from the +1 to the 0. From the +2 to the +1. So you have a discount how much the energy is. Okay?
Well, and the other thing to bear in mind is that this chemistry in the enzyme, of course, occurs in a condensed phase, right? So the question of what charge of the anion is most stable is largely academic. You want to understand the actual.
I thought that was your question at first. That's why I tried to argue the stabilization.
Because in aqueous solution, ClO2 minus would actually be solvated chlorine monoxide.
Right.
Right. So it wouldn't be chlorine 3 anymore. It'd be chlorine 2.
You need somewhere for the electron to come from.
Yeah, I get your point. I get your point. But in the actual reaction, ClO2 minus would be nonsensical.
Right. Yes.
So for your
Go ahead.
Let's continue one section.
I was just gonna, so your ClO2 2 minus, so that should have 2 unpaired electrons, right? Or you have 2 extra electrons in there, so why would your magnetization be 1?
Can you repeat this one more time?
So you have 2 unpaired electrons potentially that you added, because ClO2 isn't a neutral.
Let's Braden, ClO2 minus chlorite. Is that an open shell or a closed shell system?
2 minus or 1 minus?
No, 1 minus.
1 minus.
1 minus. They have even number.
It's close. It's close. The anion.
Okay, never mind. I see. Well, then for your other magnetizations, though, why are they negative?
This is a very good question. Also a question that I have. That's why also I'm trying to use the non-linear spin to maybe amplify the level of theory.
Well, usually if you don't have the right ground state, or if you don't have the right electron configuration, it gives you weird spin numbers. So usually that's an indication that you're not in the ground state.
Well, I guess I don't know how vast does it specifically, but there's no reason why you can't have this negative, right?
Well,
Because it could just be a beta electron.
well, magnetization is usually just a magnitude. So it should always be positive. Yeah.
So, can you go to your image of the of the formation of the iron-oxygen bond and the breaking of the oxygen-chlorine bond?
Movie?
Yeah, you can play the movie while we chat. That's cute. No, I didn't mean that. So in this process, Do you learn anything in the calculator process? Do you learn anything about the nature of that reaction? That is to say, what do the products actually? What are the products? Is that OCl fragment anionic or neutral?
Yeah, so this, I could find the answer to this. So the actual dynamics is done kind of on a low level theory, but it produces a geometry, and you can compute those geometries at a higher level. To figure it, like do a bond analysis, say using Gaussian, like a natural bond analysis, and see exactly where these electrons are kind of sitting between atoms, to see what kind of transfer is happening. That's what I'm thinking. I would be interested in is, say, like halfway through when the transfer is happening, you'll have different occupancies of orbitals between electrons, or between atoms. And so that kind of information, I think, would be really good.
From a mechanistic point of view, that would be, in my view, the most interesting question to answer here. Because I would like to know, is that OCl fragment chlorine 1 or chlorine 2? In other words, is that a homolytic bond cleavage or a
Yep. And at the beginning I mentioned that we're interested in finding that, so I will find the answer to this.
My other question is this the only productive collision that you were able to find for any orientation of the chloride coming in?
Yeah, so like I said, I only took incoming chloride from a plane, so a vertical plane cutting the macrocycle in half.
So you forced the chloride plane to be collinear with that, or coplanar with that.
Coplanar with that at different angles of approach. So it can come in the pocket, coming into the pocket of through the enzyme exterior is almost in plane with the macrocycle, a little bit under. And so the chloride has to kind of come up over in order to get to the reaction site. And so where that comes up and over and how that angle of approach is what I kind of tried to model. I assumed that it didn't come over here and approach from a 90-degree way.
Another interesting question would be, can the chloride associate with the iron in an 8:2 fashion?
Yeah, and I did not model those types of interactions. I could.
Yeah. Because this sort of speaks to the intrinsic reactivity, just the iron porphyrinate and the chloride. It would be interesting to compare and contrast that with what what we know and suspect happens, as you and I have discussed, in the enzyme active site. To see how, to sort of think about how the enzyme is actually guiding the reactivity of the substrate. That would be pretty cool. Thank you.
For the sake of the time, we need to thank Braden once again. And we have remaining 13 minutes of presentation by Christian Ulis for making good photo and for departing to for underrated poster session. Okay, floor is yours, and it will be first steps, what is possible, what is not possible, navigating in the computational research of oxidation by ruthenium complex.
So this is very preliminary. I had not had very much time. I had a lot of help with Dimitri to continue this moving forward, but we'll show what we had for results. But first off, what I'm gonna discuss is that the whole purpose of this is to look at how we're having a power crisis in the world, not at this exact moment, but looking towards the future. I found data for 2007, there was 16.2 terawatts was being used worldwide, but they're estimating through US power consumption by 2050, with the population increase, we'll probably hit 106 terawatts of energy being used per year. If we keep increasing by this rate, at some point we will hit a maximum where we could keep producing power with the current standards. So we were looking at renewable sources because as of right now we're using a lot of fossil fuels. One of the renewable sources is solar power. But solar power, you generate the power, but we're very incapable of storing this energy. So we use it as we make it, but come night, we don't have that energy anymore, so we need to figure a way to fix this. So one way of fixing this is looking at chemical energy storage, and one way is by looking at water oxidation. one way of water oxidation is that we're looking at electrolysis, and that is splitting the water with putting a current through the solution, and we will end up getting oxygen gas and protons. Then if we get to the cathode, those protons in solution will then be combined with 2 electrons forming hydrogen, which then with these can then go through the process of a hydrogen fuel cell, where we combine these hydrogen and oxygen and form water as a byproduct while giving off energy. So one way, some ways to do this, electrolysis is not a very green way. We look at the current standards of making energy because it requires a lot of power to do this process. So one way to help with this is by creating catalysts.
Your call will be disconnected.
How much energy requires to do the water oxidation. I know Dr. Rogers probably doesn't like this image because it's not showing the best of the structure. And the course time ended. Well, that was my presentation.
Why is it tied into the?
Because he videotapes them.
Tris-bip ruthenium 2 is a flat molecule?
No.
Okay.
Yeah, that's the reason I said you wouldn't like that. It was a quick and dirty structure. I know it's, I do not know the terminology of it. I have another figure right next to it of another system. We used, instead of a tris-bippy, we just used 2 bipyridines in it. Shown here. But a tripyridine would then have, this remote's evil. We'd have another bipyridine and going that way in the plane, and that is what it would be. I know I could do a better job drawing that out through ChemDraw. It's just, that's what I did to quickly show. We use this here, do not know exactly how to pronounce that because I just know tris-bippy and stuff. But this is a 2-bipyridine system, and we use that because we realized that through certain methods of doing the molecular dynamics, the bipyridines can get in the way of the water molecule getting to the ruthenium through what methods we were trying to do. First off, I was using the tris-bippy for these right here for the density states. I'm not meant the
level routine. What is precedence level routine?
Keep talking.
Yep. Okay. So.
Tell your story.
Yeah. So I created density states using the tris-bipyridine system that I got from Dimitri, and not much was a given from that. It's just a quick calculation I moved forward with, just showing the homo-lumen gaps and spin polarized density states for the ruthenium 3 cation. Just to keep this things moving forward. So as I said, we use a 2-bipyridine system here to run these molecular dynamics. We, as Dimitri calls it, evolution is just by heating up the sample just naturally and just letting the water molecules move around and hopefully strike the ruthenium. That's why we remove one of the bipyridines to help facilitate the water actually hitting. What we've realized is that it's not as easy as it seems, as you can see over the technical problems. So this is just how let's see if this one works. Yeah, okay. So we do get oxals.
Try another one.
Yeah, it's just, we do have oxygens of hydroxyls formed. I know I a little bit, but it's very quick because how much time it takes to create these. But this is with the 6+ cation. This is also to help facilitate to see if we can get the water oxidation to occur. We are struggling in getting this to occur. But to keep moving forward, I'll show it. These are also run at 1300 Kelvin. We also then had other versions of being created. And all of them, we really did not actually see any of the water oxidation occurring in a lot of these. Not entirely sure why these weren't. But what we're going to try to move forward with is what we call creationism. Okay, I'm just get this done. Creationism, which is by what Braden did, is this by taking the water molecule and then giving it an initial velocity towards the ruthenium center to hopefully facilitate the. This is definitely one of the most interesting presentations to have. To hopefully facilitate the water oxidation that occurred, we were struggling to get it with the system just by heating. We'll just call it questions at this point.
Well done, Christian. And we have 6 minutes for questions, group photo, and departing to another meeting. Please.
So, I mean, how can you interpret your creationism physically?
Physically, I didn't really think about that too much. Physically, what we're hoping for is that there's in an actual reaction solution, we have a lot more than just 11 water molecules surrounding the ruthenium catalyst. So we will probably have a lot higher chances of that actually striking than versus the evolution path of 11 molecules. So by using creationism, we just basically guarantee one of them actually hitting in a correct orientation.
Alyssa?
I just have a simple question. I must have missed it. What is your conclusion?
That we need a lot more work to really prove much. But right now our conclusion is that we are not getting any significant products of logic. If you look at very closely at some of these, we get some interesting bonds going on, especially in the 6+ cation. That I did witness a triple bonded hydrogen. Yeah. So very interesting data is shown. But that's the reason I wanted to move forward with creationism. I just didn't have enough time. Yeah, right. Just didn't have enough time to create the files and run it, and that's what happened.
What are the other 2 ligands you're putting in your ruthenium with bipyrene?
Tell by words.
What?
Tell by words.
Yeah. I believe we just took the bipyrene off and then just added hydroxyls to it.
So ruthenium gets bipyrene, gets hydroxide.
Is that what you say? This? Yeah. Okay.
11 traces this, yes.
Oh, okay. I was trying to remember what. Yeah. So it would be I know the titles are wrong. I was creating this in a
What oxidation state is that in?
So the first one was in 6, 6+.
Ruthenium 6?
It was just.
Or ruthenium is hydroxide, so ruthenium 8.
Okay. We just the reason I say 6 is because what we did is we pulled out 6 electrons from the system.
So ruthenium 6, so it's going to be net +4 cation.
Yeah.
And you couldn't get it to oxidize water?
I think I just.
What is the? Let me contribute to the discussion. What is a typical time for rate for water oxidation reaction? On which time scale?
Ruthenium 6? I have no idea.
But in most optimal situation, or what range order of magnitude?
So it's a complicated answer.
Yeah, that's a
multiple steps. Some of which are slow.
Exactly,
some
multiple
of which are
steps,
fast.
and each of steps will take substantially longer time than this 100 femtosecond short trajectories.
I think in one of the videos I did see hydrogens pop off.
But did you even see an OO bond form?
Ruthenium
6, it should be ripping electrons out of whatever the heck you throw at it.
But the way he's doing this, right? He's just defining a trajectory to the ruthenium center.
Well, that's what my hope of next.
Is the ruthenium center coordinatively unsaturated when you do that, or does it still have 2 hydroxide ligands?
It should be formed at the hydroxide ligand. We're just trying to the one you were doing, you weren't defining a path. You were just randomly fucking things at it, right?
Pretty much.
Yeah.
So, in the sake of time, we need to continue this discussion because it may seed productive research. But time is up. Let's thank all speakers. Announce them generous credit for their effort, and line up maybe near our guests for group photo. You can keep sitting and be part of the computational group. Just line up along the wall. And you can keep the.
Yeah, I would like
We're
that.
ridiculous.
I would like that picture.
Daniel, come here.
I don't know. You
Yeah,
look at
Yeah,
that.
please. You contributed to the. If you
Should I be like Nano, right?
add weight to this meeting. Can you please come?
Oh,
No, just
Would you like to take a picture?
sure. Is everybody happy?
Not really.
I have like a thought, like, can you see the picture? It's too
Okay.
loud.
Well.
Is it good?
Yes.
Okay.
Okay.
Okay. Many thanks for everyone. And we are done with class. And Jarvis has some announcement.
And we have a birthday boy here, Braden. His birthday today.
We're handing out, but I.
So we bring a cake. So
You want to delete
It
it?
melt. It must have already melted.
No, it
It's been
didn't,
2
actually.
hours. How is it not melted? I mean, it's
Doesn't go that
inside,
bad.
yeah, but it's inside chocolate, so you see, you eat
gotta
it, you're
eat
gonna
over
bite into
everything.
it, and then it's gonna.
Well, they so you nibble up and then you just drink it.